So today we will discuss about some examples on 2-degree freedom system models. We will write down the equations of motion and try to solve them. So as a first example, we will take up this problem. Let us say I have got two lumped mass points M1 and M2. So from the CG of M1 and M2, I measure the displacements and imply upon the restoring forces, call them as K1 and K2. I want to write the equation of motion. It should be equations of motion for the said problem. So I will use Newton's law to do this. I will also solve this problem or parallel problem using energy method. So I draw a free body diagram for this mass M1. I give a displacement here. So when the mass M1 starts moving towards right, this spring will restore it back, and that will be nothing but K1 of x1, because constant of a spring is essentially force per displacement. So I multiply the displacement with the stiffness, I get the force. That is what I am doing here. When I try to move the mass towards right, this spring will oppose, and let me mark that force in the opposite direction, and this force will be K2 of, simply say, x1 minus x2. So it is a easy way of remembering. When the mass moves towards right, this spring will push the mass M1 back. So I put the arrow direction, take this stiffness, and this is connected between two relative displacements. Take this as first and this as second. If you look at the second mass M2, the second mass again moving towards right, which is x2, and this spring of stiffness will try to pull it back. I simply do the same algorithm. I say K2, and I am picking up this displacement first and then putting the next relative displacement next. So these are my free body diagrams. Based on which now I will write the equations of motion using Newton's law. So Newton's law states that force is equal to mass into acceleration. So let us pick up the first case. So I will say first degree of freedom or first degree of displacement, which is x1. So which is going to be m1 x1 double dot, that is the force which is mass into acceleration of this, and it is moving towards right. Therefore I must say this is equal to minus of K1 of x1 minus of K2 of x1 minus x2. I pick up the x1 coordinate separately. I say minus of K1 plus K2 of x1 plus K2 of x2. Bring it to the left. So m1 x1 double dot plus K1 plus K2 of x1 minus K2 of x2 is 0. This is my first equation of motion. Look at the second degree. The mass is moving towards right. So again force is mass displacement acceleration. So m2 x2 double dot, and this is restoring to the opposite direction. So minus K2 of x2 minus x1. So I can say this is minus K2 x2 plus K2 x1. So m2 x2 double dot minus K2 x1 plus K2 x2 is 0. My second equation is my first equation. Let me put this equation in a matrix form. There are 2 points where the mass is lumped. One is at x1, one is at x2. Therefore the mass matrix will be a diagonal matrix. I will come to this point slightly later of x1 double dot and x2 double dot. I am just converting this in a matrix form. Plus stiffness matrix of displacement equals the force value, in my case it is 0. So with x1 the coefficients are K1 plus K2 minus K2 minus K2 K2. So this becomes my equations of motion in a matrix form. I can also write this as m x double dot plus k x as f of t, which in my case is 0. So, this is my equation of motion written in a matrix form, where mass matrix M is given by this, stiffness matrix K is given by this. So, we can draw very interesting information here. These are very important for writing the equations of motion in futuristic problems. Let us see what are those interesting information I can derive from these equations of motion. The first information I derive is writing equation of motion for a 2-degree or multi-degree using Newton's method or Newton's law of motion is simple. I can also use energy method, I will show that later. The second inference I derive is when the displacement coordinates are measured at lumped points of mass, mass matrix becomes diagonal. It means off diagonal terms are absent. 3. Usually stiffness matrix is a square symmetric diagonally dominant matrix. What does it mean is, it is a square matrix, symmetric, diagonally dominant means any coefficient of this matrix lying along the leading diagonal will be larger than any other element in that row. So, diagonally dominant, it shows me that inverse of this matrix exists. So, inverse of K is what we call flexibility matrix. So, inverse of this matrix exists. And of course, fourth and very simple observation is that the size of this matrix will be of order n, where n is the degree of freedom. So, 2 by 2, therefore, it is 2. These informations are very important. You will see that this is very important information which I will use later. So, I want you to quickly write the equations of motion for the second problem which I am giving here. I will give you 5 minutes time. So, m1, m2, x1, x2, 2k, k, 2k. So, the equation of motion is given that is how it is obtained. Let us do one more problem. I want you to write the equations of motion for this problem. I can draw a free body diagram in helping you. If this mass moves down, this spring will try to restore it back. So this will be K1 of x1, whereas this spring will try to push it up. So it is going to be K2 of x1 minus x2. That is for the mass m1, and so on. Same way you can do further. If you do it for the mass m2, move it down, the mass will move down, this spring will try to push it up, that is going to be K2 of x2 minus x1. Always pick up the first value as the place where you are applying the inertia force. When you got relative displacement, I have picked up the first value as the place where the inertia force is applied when there is a relative displacement. When there is non-relative displacement, simply use that value, that is all. It is a very simple algorithm. So I will get the equation of motion as So interestingly, one can notice that when the mass is lumped at the same point where the displacement degrees of freedom are measured, the mass matrix will be diagonal. We will see an example now. If I violate this, what happens? Before that, let us do one more problem of writing equation of motion using energy method. So I will use energy method now. To write equation of motion for multi-degree. Equation of motion in energy method is given by Lagrange S equation. Now what is Lagrange S equation? The Lagrange S equation says d by dt of partial derivative of kinetic energy with respect to qi dot minus partial derivative of kinetic energy with qi plus partial derivative of potential energy with qi plus partial derivative of dissipation energy with qi dot should be given by or equal to qi, where capital Qi is the forces in generalized coordinates of I. Whereas kinetic energy, potential energy and dissipation energy are given by the following equations. Kinetic energy half m xi square, potential energy half k xi square, dissipation energy half C xi dot square So, use these expressions now and let us try to write the equations of motion for a 2-degree freedom system as I am going to show you now. So, we will neglect the frictional forces between the mass and the contact points. So, kinetic energy half m1 x1 dot square plus half m2 x2 dot square, potential energy half k relative displacement. So, we will use Lagrange S equation to write down the equations of motion based on energy method. The Lagrange equation says you first find the partial derivative of the kinetic energy with respect to each one of the degree of freedom. So, let us try to do that first. Potential kinetic energy with respect to, instead of qi I am using my coordinate generalized as xi. So, dou x1 dot, that is what I am going to do here, partial derivative, because kinetic energy is a function of x1 and x2 both. I take a partial derivative of this. This will become simply x1 dot. Similarly, dou kinetic energy of dou x1, which is the second term here, obviously it is going to be 0. The third term, potential energy by dou x1, that is the third term here. So, this is going to be minus of k of x2 minus x1. Is that okay? Partial derivative of dissipation energy with respect to x1 dot is 0 because dissipation energy is not considered. I am not considering any frictional force between the mass and the plane of motion. Similarly, I can do for the second case. So, dou kinetic energy by dou x2 dot is m2 x2 dot, dou kinetic energy by dou x2 0, dou potential energy by dou x2 is k of x2 minus x1, dou dissipation energy by dou x2 dot is set to 0 because of the same reason. I will remove this. So, for first degree of freedom, I must say d by dt of this equation where all I will become 1. So, I must say d by dt of this, which will give me m1 x1 double dot. I am differentiating this with to time, minus k of x2 minus x1 will be 0 because there is no qi acting in the model. So I should say m1 x1 double dot plus k of x1 minus k of x2 is 0 will be my first equation of motion for this problem. For the second degree, again d by dt of this expression with respect to the second degree of freedom which I have here, which will be m2 x2 double dot plus k of x2 minus x1 is 0. I am putting 0 here because there is no q2 term in the given model. So I should say m2 x2 double dot minus k of x1 plus k of x2 is 0. I can convert this in a matrix form as m1 0 0 m2 of x1 double dot x2 double dot plus k minus k k of x1 x2 as 0, which is my equations of motion in a matrix form. You will again notice that mass matrix becomes diagonal, stiffness matrix becomes diagonally dominant and symmetric and square because I am applying the mass lump at the same point where I am measuring the displacement. Let us quickly check whether I do the same problem in Newton's law and get the same equation of motion. I will remove this. So if you take mass m1 separately and draw a free body diagram, the mass moves to the right and this spring will push the mass back, which will be x1 minus x2. As I said already, take the component of the stiffness here, use this coordinate first when it is relatively connected. Pick up the second mass m2, the mass moves to the right, the spring will bring it back, so it is again k of x2 minus x1. It is very simple algorithm to remember. So draw the free body diagrams and then write down the equations of motion based on Newton's law F is equal to ma and check whether you are getting the same equations as you already have. So m1 x1 double dot is going to be minus of k of x1 minus x2, which will give me m1 x1 double dot plus k x1 minus k x2 as 0 is my first equation, as same as what I am having here. Similarly m2 x2 double dot is going to be minus of k of x2 minus x1, which will give me m2 x2 double dot minus k x1 plus k x2 is 0, which is as same as the same equation which I got here. So you can adopt any method for writing equations of motion. We have demonstrated it using a Lagrange S equation, which is energy principle, as well as Newton's method, which you already know. But generally equations of motion are comfortably written using Newton's method because they deal with forces, whereas Lagrange deals with the energy principles. When you want to minimize or optimize or talk about response control in terms of energy mechanisms, then one can write equations of motion using energy methods. Otherwise Newton's law, which is adopting the force technique, will be simpler. Remember, very interestingly here, it is not depending upon which domain you want to solve the problem, okay, and these are all time variant x1 double dot, they are all time variants and so on. Any questions here? So one can solve or one can write equations of motion in any preferable method, except the few which we discussed in the first chapters on single degree of freedom system models. Now throughout these examples we understood that when the mass matrix or the mass is lumped at the point where a displacement is measured, mass matrix becomes diagonal and diagonally dominant, and off diagonal terms are generally 0. but is there cases or are there any case where we do not have the lumped mass at the point where the displacements are measured. We will take an example exclusively on that form and see how to derive mass matrix for that situations, because very important in our offshore structural systems it is not necessary that the force can be applied at the same point where the mass is concentrated, or displacements need not be measured in the same point where the mass is concentrated. I give you a very simple example. I have got a floating let us say FPSO, the CG of the floating FPSO is somewhere located above the mean sea level, let us say, but I do not want to measure the displacements at the CG of the FPSO, I want to measure the displacement of the deck. It means I am not interested in measuring the degrees of freedom or marking the degrees of freedom at the point where the mass is lumped. So what will happen, how do I compute my mass? Okay, not necessarily you should always want to know the displacements in the place where the mass is lumped, and there may be instances where the force may be not applied at the same point where the mass is said to be lumped. For example, aerodynamic forces, you got the derricks, you got let us say cranes where wind force are acting on the top side of the structural system in offshore, whereas the CG of the system is not at the point where the force is acting. Therefore you would like to measure the displacement at the point where the force is acting because you want to know the maximum displacement, but your mass is lumped at different point. What will happen in such situations? How do I write my equation of motion, because I do not know how to derive my mass matrix? In this case it is simple because mass matrix becomes diagonal. There are cases where stiffness matrix also will become unsymmetric. Let us see their special cases as we move on. In general stiffness matrices are generally square and symmetric. They may still remain square but they may not remain symmetric. There can be axisymmetric terms which will influence the response behavior of the platform in certain cases, we will see. I have a very interesting question for you, let me see who can answer this. In Lagrange's expression I have one term which is dou kinetic energy by dou qi, but kinetic energy is always a function of velocity. Why this term exists in Lagrange equation? Okay, kinetic energy is always a function of velocity, but why I have a term here? Think it over. Any doubt? We will move on to another problem where we will violate this standard and see what happens. Take up a problem like this. Example number, is it 5 or 6? Okay, see that will never settle. Okay, this is a democratic country, I think we should take voting. I have a deck which rests on a system which is supported by springs. It is a very typical model. There can be practical applications of this model, I will come to that slightly later. Let us say this is my mass center, the total mass of the system is capital M, total mass. So I have forces applied here as Pt and P theta, these are the forces which are applied on the system. Obviously these forces are expected to be applied at the mass center, whereas I am crazy to measure the displacements at these locations where the spring is connected. So I am violating the system saying I do not want to measure my displacements at the point where the mass is lumped. What will happen to my equations of motion? This is my K1 and K2, I am deliberately varying them so that we see the derivations clearly. So to find the stiffness matrix first, it is an axial stiffness. Okay, to find the stiffness matrix first, so first step is to find stiffness matrix. What will be the size of this matrix? Because there are 2 degrees of freedom. Okay, not because there are 2 sets of forces acting, 2 degrees of freedom. it also improvises a very important conclusion. Degrees of freedom are not the points where the mass is lumped. Here I have got only one point where the mass is lumped, I got 2 degrees of freedom. I think we have cleared it very carefully in the previous definitions. So we can always have a shortcut saying mass points are said to be the degrees of freedom, but it is not true always. For example, in this case, so I want to derive the stiffness matrix for this. So I give as usual unit displacement at this end, I put delta as 1 and do not give any displacement here, it is going to be a linear line because it is actually a hinge. So the force what I will get which is responsible for causing this unit displacement is my stiffness, which I call as K11, force in the first degree because of displacement given in the first degree itself, and obviously this will be equal to K force in the second degree because of displacement given in the first degree. Remember, stiffness matrix is always derived column wise, the second number will be always same, it is always column wise. Okay. Flexibility matrix is always row wise. Obviously from this figure one can easily understand that K1 is directly equal to K, okay, because that is a stiffness, because stiffness by definition is force for unit displacement. I am giving unit displacement, therefore this value will be directly equal to my K1, and what will be my K21? No displacement, no force, is it not? Similarly, and what will be this coefficient called K? Always the second coefficient or the second number will remain same because column wise. So K22 will be equal to K2 and K12 0. My K matrix now is going to be K1 0 0 K2. Now interestingly you see what happened to my K matrix, it has become diagonal. Okay. Technically in dynamics literature people call this as coupling and uncoupling of stiffness and mass matrices. Okay. We will come to that later, application parts, the terminologies will come slightly later, but what you can interestingly see here is stiffness matrix will become diagonal whereas mass matrix will not become diagonal. If they become diagonal, what will happen? The system will become okay. I will remove this, think it over. If stiffness and mass both becomes diagonal, what happens? See, if these questions can be answered extempore, I think you can directly take the third module of this classes. So I want to now derive the force vector. Now one may wonder, so why I am deriving the force vector? Remember very carefully here, I am applying forces at the point where the displacements are not measured. So I want to find what is the equivalent force of these components at x1 and x2. In the previous examples we always assumed that either the force were 0 or the force are expected to apply at the point where the mass are concentrated, and fortunately the points where the masses were lumped, we had also the degrees of freedom measured. So we had no confusions at all in the previous examples, but here we have got second confusion that the force are not applied at the point where displacements are measured. I will work out another problem where displacements are measured at this point but the force are applied at this point. Okay, we will talk about that, is also possible. You must visualize the physical importance of these problems, they may look like a simple application, I will come to that once we finish this. I want to find the force vector. What would be the basis to find out this? Okay, I pick up this deck and apply, let us say PT, and the component of this will be, because of symmetry, PT by 2 and PT by 2, and I apply P theta which is clockwise. So there is a clockwise moment, I would like to make an anti-clockwise couple to counteract this, that is nothing but P theta by L, where L is the distance between these 2 points. So now I have a vector P, the force vector, which is nothing but minus Pt by 2 minus P theta by L. Similarly, the second one, if you look at, it is going to be minus Pt by 2 plus P theta by L. It is negative because the force what I have here is opposite to that of my direction of displacement. And so on. So I got my force vector, which is a vector of 2 rows and 1 column. The third step will be to derive my mass matrix. Any doubt here? I will remove this. Mass matrix. I will use a similar principle as that of K. Use similar principle as that of K. I am taking very great care to write properly, but my handwriting is extraordinary, so you have got to follow that carefully. It is one of the non-identifiable characteristic of my this thing, so you have got to follow it carefully. So keep all your organs on. So I will use this, I will give unit acceleration. I call this as, let us say, let's say x1 double dot as unity, and set this to 0. So when you do that, you will create mass into acceleration, and this will be opposed by 2 reactions. I will call this as mass value 2 because applied at 1. I call this as mass value 1 applied at 1. Same concept I am using for stiffness, similar one. So let me take moment about this point. So this is going to act down. Take moment about this point. So M21 of L will be half L height of M by L. I am finding out M per unit length now. M is the total value, is it not? And this is the force, 1/3 of L, that is the CG of this from here. So this will give me M21 as, so L goes away, L goes away. Is it M by 6? So M11 will be the total area of this triangle, or the total force, or the total inertia force minus the reaction force of M21, which will be half L height M by L minus M by 6, which will be M by 3. Is that okay? Now I want to find the second row, second column of the mass matrix. Same algorithm apply here, call x2 double dot as unity and apply these forces and find these reactions at the distance L and so on. I call this value as M M22, I call this value as M12. So can you quickly find out these two values? So taking moment about this point, so M12 of L will be equal to anticlockwise of half base height M by L of 1/3 of L. This gives me M12, L goes away, L goes away, M by 6, and M22 will be half base height of M by L minus M by 6, which will be M by 3. So my mass matrix now becomes M by 3, M by 6, M by 6, M by 3, which is not a diagonal matrix. Okay. So by this way we can keep on working out all the probabilities of putting the forces elsewhere, measuring the displacements elsewhere, and keep on doing it. Now what is the practical significance of this problem? There are many applications of this particular example. Number one, this can be a problem of a seismic isolation where I rest my whole mass on a system supported by springs. So it is a seismic isolator. You may say why seismic? It can be even response control mechanism. I can give a very simple example of this practically. You must have seen in olden days people have been using typewriters. Typewriters are normally not kept on the desk directly on the table, because what will happen when you keep on using the typewriters, because of the vibration when you are using the typewriter, the legs of the table will get shaken. So they put a pad and keep the typewriter over that. Okay, that is a vibration absorber. Similarly here response control, I can say vibration absorber. The third is an interesting geotechnical model where the superstructure is resting on the foundation on Winkler springs, where Winkler springs are represented as equivalent series of springs like this. So there are many practical applications of the line diagram what you see here, whereas the force are all applied to the mass center, the displacements need not be there at the mass center. Okay. This also proves very interestingly one thing to us, that the degree of freedom is nothing related to the mass point. Here it is 2, whereas the mass is said to be constant only at one point. So all confusions related to degree of freedom is point where the mass is concentrated are all gone. We have already defined it very carefully and very clearly that it is nothing related to mass concentration lumped mass points, but crudely one can remember like this, that wherever the mass are lumped, these are the number of degrees of freedom, but not always, you see here. So be very careful in marking them, and always visualize the problem, where are you measuring your displacements, where the mass is concentrated, where are the forces applied. So always equation of motion cannot be simply the same form what we saw in the previous examples, it can slightly vary. So be very careful in marking these elements of or the dynamic characteristics of your problem. So we have any questions here? I think we will stop here.